This week, we're going to be taking a look at what we can know about the slope of a function over a particular interval, given certain piece of information. So take a look here, and you see that we know two things about this particular function. Well, besides the fact that actually it is a function, right? The first is that f is continuous over this particular interval. The second thing that we can know about this up front is that our function f is differentiable over this interval as well. So based on that information, what can you know about the slope of the function between those 2 points? That is, over this interval from a to b, what can we know happens in that slope? Do you know that the slope will ever reach this value? You know, this positive value in this particular case. Not necessarily in this one. Could it reach this value? It could. Now, does it have to? Not necessarily. What does it actually have to hit? Well, if we think about any different kind of function that is both continuous and differentiable at every single point between a and b, we end up with something that looks like that, or we could end up with something that looks like this, or this. All of those include one particular slope value, and that is this one. The only slope that must absolutely hit someplace between a and b is the exact slope between a and b. And so while we can say that yes, it might also do something like this and so hit other slopes, we don't know that it actually will. The only slope that we know that it will contain is this. Now, if it's not just a straight line between a and b, here's an example where we can see in blue here, this is the slope between a and b, and we can see that our curve does hit that same slope up here. Or it might happen multiple times, where you can see where it would hit that same slope between a and b here and here. But we do know that the graph is guaranteed to hit that exact slope between a and b at some point between a and b. Maybe once, maybe more than once. But this is actually a theorem that has some other implications. But for now, we're just going to be looking at the theorem itself. So this is going to need to go into your notes. We're talking today about the mean value theorem. All right, so hopefully you've gotten all this written down. Pause it if you need to. So just taking a look at a little bit of the verbiage that's being used in here, you'll notice that it says there is a number c in the interval a to b. This number c is just used here as the value at which it hits that slope. So c is actually an x value. All right, and then you'll notice that we have this big formula down here. This should not be a new formula to you. Notice that basically all this is the slope formula. So this whole part over here is just how we calculate slope. So we're saying that the derivative will at some point equal the slope. And that's all that's representing there symbolically. So next up, we're going to go test this theorem and see how it actually comes into use and how we can actually use it. Take a look through this problem, read it through, and as always when working these types of problems with the video lessons, by all means pause it long enough for you to digest what's going on before I start talking at you about it all. All right, so in order to be able to find the values that satisfy the mean value theorem, we need to do two things up front. And that is we need to first figure out if it actually satisfies the mean value theorem's hypothesis. So that is two different criteria. We need to decide that it is in fact continuous over the interval and that it is differentiable over the interval. Now in this case, our interval is from -2 to 1. Okay, but is it continuous on that? Many of you I know are probably saying, well, how would we know? How do we prove that? Do we have to go through this big long process? Thankfully we don't, because this is a polynomial function. We know that a polynomial function is continuous over all numbers in its domain. That is just a fact that we know about polynomial functions as well as many other functions. We also know that it is differentiable over all of those numbers in its domain for the same reason, because it's a polynomial. It has no asymptotes, corners, or holes in it. So now that we know that it is continuous and differentiable over the interval from -2 to 1, we now can go ahead and find our value of c. That is the x value where the derivative equals the slope. Notice that in order to do this, we have to do two things. First, we have to find the derivative. And so I find my derivative function, and then the other thing I need to do is I need to find out what the slope is between the endpoints. And so we're going to do our normal slope formula. Basically, it's delta y over delta x. And remember that when we're doing this, that these values here on the top, they are the y values, just the y values. So I'm plugging them back into the original function up here. I'm not plugging into the derivative. And so I plug in those values of 1 and -2 into the original function. I got 7 and 1. And then I go ahead and just simplify my fraction down. And I get a slope of 2. So going back, remember that what we're trying to do is we're trying to find c, which means the location or locations where the derivative equals the slope. So that means I now need to take the derivative that I found earlier and I'm going to set it equal to the slope that I found. So I'm going to turn this into 2 equals 2x plus 3, and then we solve that from there. And we find that x here would equal -1/2. That is our c value. That is what we are trying to find. That is the x value at which the derivative has the same slope as the slope of the line between our two endpoints. And so we're done. Now going back to the notes that you took earlier, this is the same information except we got a little extra statement here at the end. That this theorem, the mean value theorem, actually also has a special name in the particular case in which f prime is set equal to 0. And that is Rolle's theorem. So this should also go into your notes. But as you put this in there, you're going to notice it's very, very similar to mean value theorem. Basically, this is just a special case of mean value theorem. The only difference between this and mean value theorem is that we have to also know up front that f of a equals f of b. In other words, the y-coordinate at point A is going to be the same as the y-coordinate at point B, which means then that the slope between those 2 points would be 0. So this is just a very specific case where the slope that we're looking to equal is 0 instead of just any old random number. But again, please make sure that this is in fact in your notes before you proceed. We are now going to practice using Rolle's theorem on this particular function. All right, so again, kind of look it over, have an idea about how you'd approach it, then we'll go through it together here. All right, so in order to be able to use Rolle's theorem, this first part where it says to verify that it actually satisfies the hypotheses of Rolle's theorem, that means we have to check these 3 things. So first of all, is it continuous on our interval here? Well, notice what our function type is. It's a polynomial. No asymptotes, no holes. Therefore, it is not only continuous, but it is also differentiable. So therefore, we can say yes and yes. And then the last thing we need to check, specifically because this is Rolle's theorem, is we need to check and see, does f of a equal f of b? So this means we actually got to plug in the endpoints from our interval here and see what the f value is for each one. So I'm going to be doing f of -4, and I'm going to be doing f of 4. When I do so, I end up getting that f of -4 is 204, and f of 4 is -308, which means they're not the same. Now, all I needed was for these two numbers to be the same for this to be the case. They don't both have to be 0 or anything, but they do have to be the same as each other. And in this case, since they are not, this one actually does not meet the requirements of Rolle's theorem. Now, if we were asked to use mean value theorem, we could do that because this would not be a factor here. However, because this is talking about Rolle's theorem, we can't do it. And so this one would just be saying, well, we cannot satisfy it, therefore we're done. And so with that one done, let's go on to the next example. So this question is the same as the last question, except we have a different function and interval. So we're going to look to start by verifying that it satisfies the hypotheses of Rolle's theorem. And again, do you know what those are? Are you starting to remember them? Hopefully you're coming up with that our function needs to be continuous over the interval, differentiable over the interval, and because this is Rolle's, that f of a must equal f of b. So, first of all, is it going to be continuous and differentiable over the interval? And because this is another polynomial function, the answer is yes. All right, so now that we know that, we now just have to do the math to check this. We need to see, does f of a equal f of b, which means I actually need to figure out what f of a is, which is going to be f of 3, because a is whatever that first number in our interval is. And then we have to figure out what f of 8 is, because that's going to be f of b, and b is whatever the second number is in our interval. And so we're going to plug both of those now back into the original function up here. And both of those end up giving us 6. Now remember, they don't have to both be 0, they just have to be equal to each other, meaning that the slope between those two would be 0, because if that's at a height of 6 and that's at a height of 6, then our slope is going to be 0, and that's what we want. So yes, this one does work. So having now verified that it satisfies the hypotheses of Rolle's theorem, we now can actually do the work. That is, to find all the numbers that satisfy the conclusion of Rolle's theorem. Now the conclusion of Rolle's theorem is that at some point between the intervals, it's going to have a slope of 0. Same idea as mean value theorem, just specifically in this case we're dealing with a slope of 0 rather than a slope we have to calculate. So that means I need to find my derivative. So we're going to do f prime of x first here, and that's going to be 2x minus 11. And we want to set that now equal to 0. So we're going to go 0 equals the 2x minus 11. And now solve that for x. And so x equals 11 halves, or 5.5, or 5.5, however you want to write it. That is our c value. And so that is our final solution. Now, if you're like me, when you see these types of problems, you might be looking at an answer like that saying, okay, great, it happens at 5.5. Why do I particularly care? What's the big deal about the fact that at some point between those two endpoints, we actually end up getting a slope of 0? How could this really be used? And so I actually wrestled with that for a while, but eventually I started seeing a few applications, and one of them is actually one that you have already seen. On last week's assignment that I had you do, the last written assignment that you did through Google Classroom, I gave you this problem. This is the exact same problem that you saw before, where we're talking about average speed cameras. Most of us are familiar with police trying to catch speeders by using their radar guns. But another technique that is used in Great Britain as well as other places is the average speed camera, where basically they have two cameras set up, a ways away from each other. In this particular example, they are exactly 1 mile apart, our two cameras are. And it just says, okay, you cross camera A at this time, and you cross camera B at this time, so therefore we can calculate how fast you are going between those two. And the question was, in this particular case, that someone was claiming that even though his average speed was over the speed limit, because he went 1 mile in exactly 60 seconds, that would be 60 miles per hour, even though his average was 60 miles per hour, he's trying to claim that he never within that time actually went over 50. He's saying, okay, well maybe, something weird is going on with the calculations. And, when we first read this, our inclination is to say, well, no, that's impossible. But can you prove why? How could you possibly actually justify it? And this now brings us back to the mean value theorem that we were taking a look at today. Because the mean value theorem actually can prove this. So if we want to think about this problem in the context of the mean value theorem, the first thing we think about is, well, could we know that it's continuous and differentiable between those 2 points? Well, if you think about the travel of a car, does it ever, if you're graphing it or something like that, would the graph of this car's path ever have a jump in it, or an asymptote, or a hole? Well, it's not like the car is driving along and then all of a sudden it jumps over, right? It's impossible. Even with our speeds, it's impossible to jump straight from, say, 60 miles per hour to 30 miles per hour. You can get there very quickly, but you cannot go there immediately. There is always a change of period there. And for that reason, it is in fact continuous and it's differentiable between those 2 points. He would have to disobey the laws of physics in order to change that part. Now in the mean value theorem, we are then told that we're trying to figure out what value of c would satisfy this. Well, what's playing the role of what in this case? Well, our slope over here, that's the average, right? That's what is it doing over the endpoints. Well, we actually know in this case then that if we calculated the slope, that is how fast he was going between those 2 endpoints, he went 1 mile in 60 seconds. So he went 60 seconds, 1 mile. Notice that's how we get the 60 miles per hour. And so that's going to be 60 miles per hour there, which means that at some point, the derivative must have equaled 60 miles per hour. Okay, well, what's the derivative? Well, notice that when we found that 60 miles per hour, we were using his position. We were basically looking at how did his position change over that mile. And so then, what's the derivative of position? Velocity. And so then, therefore, we could conclude that his velocity at some point, now we don't know where that point is because we don't know his position function, but we can know for sure because of the mean value theorem that his velocity did in fact hit 60 miles per hour at least once during that time period. And therefore, we could conclude that no, his argument cannot be possibly true, that he never actually exceeded it, even though the average was higher.